Okay, um, uh, I would like to thank the organizers for inviting me to this workshop. So as I has said, I will talk about basically how to apply some ideas from functional analysis to understand the problem in algebraic dynamics, and more specifically, how to iterate rational maps on projective varieties and look at certain sequences that are called degree sequences. So let me start with to tell you what I will say about today. So first, I will talk about the problem that I'm interested in. So um, then I will tell you a little bit about what has been done so far, and then I will go into the subject, which is this. To solve, to understand this problem, I will use some ideas from function analysis on a space called the b-divisors. So those are divisors, generalization of divisors, and the terminology comes from Shokurov in the and it was used in the minimal model program, and here we use it to do some dynamics. So let me start with the problem, the setup that I would like to use today. So you start with X, the complex projective space of dimension D. You can think of this or maybe a smooth projective variety defined over C. You start with omega, an ample divisor on X, and I will take my dynamical system, so the one induced by a dominant rational F, so given in homogeneous coordinates by D plus 1 polynomial, which are homogeneous of the same degree with no common factor. Okay, and the quantity that I'm interested in is simply the so-called algebraic degree of F, and it's the degree, the common degree of my polynomials. Okay, and I call this algebraic degree, and I write it degree 1 of F, because geometrically, basically, it is the degree of a generic hyperplane, the preimage of a generic hyperplane. So my question today is to study the sequence. So you take n converging to infinity, and you look at the degree 1 of f to the power n. So the algebraic degree of the nth iterate of f. And I want to know the asymptotic sequence of yes. Okay. So now let me start with so as I said, the algebraic degree can be interpreted geometrically as the degree of generic hyperplane by the preimage of a generic hyperplane. Let me go further and go more geometrically. You can look at the degree of the preimage of a codimension K hypersurface. So how does it work? Well, you take a codimension K hypersurface. Well, it can be represented by omega K, and then you resolve the graph of your rational map. So you look at the desingularization of the graph of f in x times x, and it gives you gamma tilde. And basically, you can take the preimage by the second projection. So this gives you something of codimension K, and take its image by pi1 inverse. So this is basically like the preimage of a codimension K hypersurface. It has a certain degree, and then you apply Bézout. You calculate this degree by intersecting by enough hyperplanes to get a number. So this is the degree K of F, and it measures how F acts on codimension K hypersurfaces. Okay, so it's the generalization of the algebraic degree. So when K equals 1, you recover the former formula. And the first thing you can say now when you want to did you see something went wrong here? Oh, do you see my screen again?
Yeah, it's okay. I can see your screen.
Okay, okay. I think there was a problem. So as I said, so you get this formula that is the degree of the preimage of a codimension K hypersurface. And so now I want to iterate this. So the first thing you can say is that actually the sequence of degrees of Fn is sub-multiplicative. So you can define the so-called case dynamical degree, which is the asymptotic ratio of this quantity. Okay, so for each k, you fix each k between 0 and the dimension d, and you iterate Fn, and then you look at the degree of Fn at the power 1 over n. And it gives you a number, and it's an invariant, a dynamical invariant that is called the dynamical degree of F. So for each k, you get one of those numbers. So it is a finite number. Okay, so now that you have the quantities that interest me, let me try to explain how you can understand them in the most simple case. So when F is a regular map, so not rational yet, but so when F is a rational map, everything unfolds with linear algebra basically, and so you can understand everything. So let's start with codimension 1, the space of divisors. So you're going to look at the space n1 of x, the numerical group of divisors. So it is the group of divisor cycles modulo numerical equivalence, and I say that two divisors are numerically equal if for every algebraic curve they intersect and give the same number. Okay, and you can define the notion of numerical equivalence for codimension k cycles using the same formula, basically, by intersecting with the appropriate um, um, the finite dimensional subvarieties with appropriate subvarieties. And the observation that I'm going to tell you today, is that, if the easy observation is that the pullback, when F is regular, you have a pullback on cycles, and it induces an endomorphism of this finite dimensional vector space. And the dynamical degree that was computed at the asymptotic ratio of the degree sequence is the spectral norm, the spectral radius of this pullback operator acting on nk. Okay, and so because of this, we see that, the degree sequence is kind of constrained. It has to grow in between, here, it has to be a growth in between a polynomial growth or a polynomial times exponential. Well, this is when you get Jordan blocks of your endomorphism, of your matrix. Okay, so this is somehow the motivation of the main conjectures and problems in algebraic dynamics when you study these degrees. So this I call it a folklore conjecture because it's something that was written, but it's somehow very hard to tackle this problem. So it says that, okay, if this happens for regular maps, then it should happen for rational maps. So there should be a growth in between pure exponential and polynomial times exponential when you take any dominant rational map. And so these conjectures were, how do I say, and moreover, this dynamical degree here, we see that they are algebraic integers because they are, how do I say, the zeros of the characteristic polynomial of a matrix in the regular case. So you can ask two questions. First, if there is a growth that you understand, and that the dynamical degree is a specific number, maybe is it always an algebraic number? So in dimension 2, it was very there were some cases that were understood. So by Jung and Friedland-Milnor, if you look at automorphism of C2, so polynomial automorphism, then you can check that the first dynamical degree here is an integer, and this you always have this growth that is a exponential or polynomial times exponential. For more generally, for birational maps, it's a theorem of Favre on surfaces that says that if the lambda1 of f is not an integer anymore, but it becomes an algebraic integer, and this conjecture still holds. Okay. Some other cases in dimension 2 that I want to emphasize is, well, you can go further. Instead of looking at invertible maps of C2, you can go and look at polynomial maps, not necessarily invertible. And then it was also checked that lambda1 is also an algebraic number, and this conjecture holds. And then the story recently became more complicated because now in 2020 there's a counterexample of a rational surface map such that lambda1 of f is not an algebraic anymore; it's a transcendental number. So somehow this viewpoint that we had with regular for regular maps kind of falls when we think of rational maps, even on surfaces. So okay. And now the last theorem that I wanted to emphasize today is this theorem. So you start with the surface, and you suppose that there's this strict inequality condition on the dynamical degree. So the first dynamical degree square is bigger or equal than the second dynamical, strictly bigger than the second dynamical degree of f. Then you have a purely exponential growth of the degree sequence. So this, in fact, this condition comes from the log concavity of the intersection numbers. So the log concavity tells you that basically the degree of f squared is bigger or equal than the degree, the second degree. Sorry, my bad. And when you take an asymptotic, you apply it to Fn, this tells you that lambda1 square is bigger or equal than lambda2, so the asymptotic ratio. And here, it's a strict log concavity condition on the Khovansky-Tessier inequalities that you asked. So this is what is known in this case of surfaces. So let me tell you now, if we try to go further, so in dimension D, bigger or equal to 3. So the known case are the following, and you see that there are less and less things that are known. So we know everything for regular maps, and then people have studied particular cases. So cases where, for example, your map has a particular form when it's called monomial. So for this case, we know these conjectures, and in other cases, well, we know it for automorphism of C3 with a small algebraic degree, with algebraic degree smaller or equal to 3, and in the last 3 known studied cases, in fact, there are studies of either particular subgroups of automorphism or a study of very slow growth. So when you want to know when the degree grows very, very slowly, and there are works on it.
But can I ask the first line? So the first line lambda kf is spectral radius, right? It's not the known.
Yeah. I always denote the spectral radius as like this, but yeah, sorry. Okay, the spectral radius row of f star acting on nk of x. Yes. Yeah. Okay. My bad. Okay, I should write things differently. Okay, yeah, it's the spectral radius. I'm sorry. You're right. Oh, okay. So basically, we know less because in higher dimension, the techniques that were used in dimension 2 kind of don't apply directly here. And so let me go to the next thing I want to the theorem I want to advertise today. So so it's a joint work with Charles Favre, and we assume that X is a smooth projective variety of dimension D bigger or equal to 2. You take a dominant rational map that satisfies the strict log concavity condition, so lambda 1 square strictly bigger than lambda 2. Then there exists a constant such that you have a purely exponential growth for the degree sequence. Okay, and as a consequence of our method, we basically get a corollary, that is that if you have a polynomial automorphism of C3, then both lambda 1 of f and lambda 2 of f are algebraic numbers. Okay, and I will focus on this first theorem and how to obtain, how to give you the ideas for this statement here. So let me comment a little bit the conditions of the theorem. So you have this condition, lambda 1 square bigger or strictly bigger than lambda 2, and to understand it, you can look at some very simple cases, and you assume X is an abelian variety and F is an endomorphism on X. So in the regular case, you understand everything, because basically the condition, you can look at the eigenvalues of the pullback of F on the space of divisors, and you have that if you order the eigenvalues by the norms, then lambda 1 square is basically rho 1 square, and lambda 2 is rho 1 rho 2. So the condition lambda 1 square strictly bigger than lambda 2 is basically that you ask that lambda 1 is here, the eigenvalue lambda 1 is here, and all the others are in the disk of radius, square root of lambda 2. Okay, so you get this condition, and it's a picture that I want to remember. And even more, in fact, what will happen is that in this case, the eigenvalue lambda 1 will be simple. So you have a unique eigenvector for the eigenvalue lambda 1. So let me tell you a very complicated argument to show this, and it comes from the Hodge index theorem. So let me assume here that F is regular, and with the Hodge index theorem, I'm going to tell you that lambda 1 of F, the eigenvalue, will be simple. So this simplicity. So the proof goes as follows. So you assume you have two eigenvalues, lambda and mu, bigger than square root of lambda 2 of F, and you take alpha and beta, two eigenvectors for those two eigenvalues. So what you're going to do is multiply them. So you see, you multiply them, and what happens is alpha times beta. This has somehow, you have two possibilities. You can pull back the product alpha times beta, and if you pull it back, the product, you get mu times lambda that appears. So mu times lambda at the power n if you pull back by Fn. On the other hand, because Fn acts on the codimension 2 space and the spectral radius is controlled by lambda 2, then you get a lambda 2 to the power n here. So the condition lambda 1 square strictly bigger than lambda 2 implies that basically alpha times beta and alpha square beta square equals 0. Now I'm going to apply the Hodge index theorem on surfaces. So how does it work? So you take any generic surface and you're going to look at alpha restricted to S. So now you have a divisor on a surface S. and you look at beta restricted to S, and the Hodge index theorem on S tells you that alpha and S, alpha restricted to S and beta restricted to S are proportional. So for every S, you have a constant of proportionality. And so a simple argument tells you that, in fact, the constant of proportionality is the same for every S. So alpha and beta are proportional. So from this, in fact, you see that the main idea is to be able to restrict to surfaces. If you know how to restrict to generic surfaces, then you can show the simplicity of this eigenvalue lambda 1 on the space of divisors. So there's this restriction argument that I want to emphasize. Okay, so now let me go to now I'm going to go beyond the regular maps, and so let me start to tell you, okay, how we are going to mimic what happens in the regular case, but in the general in general. So to do this, what we're going to do is, okay, we're going to see what the problem is. So the problem is, for regular maps, we could pull back like this. Here, we have a rational map, so the pullback is not really well behaved. So basically, you can desingularize the graph of your map, and you can first always pull back by the by this map that I denote V1. Yes. By the map that I denote V1. And the problem is that if you look at everything, if you push down again, then you lose the functoriality of the pullback, because you cannot, the push forward is not functorial, does not have good functoriality properties. So when you start with the divisor omega here, you can pull it back once, but then if you want to iterate twice, you have to pull it back again. So the way we do it is we do some kind of limiting construction. Is like, okay, you look at the induced map by F on X1. So this is the map that I denoted F1. So you start with your divisor here, you pull it back, you get a divisor here. Now, if you want to pull it back again, then you pull it back by resolving the map F1. So taking the desingularization of the graph of F1, and you get a model, a birational map, a birational model X2, and two maps onto X1. And you continue the construction and so on, and so you will get X3, some birational map here, and some induced mapping here, diagonally, and so. And so this is the space of somehow my tower of blow up. I construct a tower of blow up that depends on F. And now I can look at the space of divisors. So we know what's going to happen. So I denote by nk of x the space of somehow cycles that live on every model, on each model of my tower. So and with the compatibility condition. So I asked that if I have one class that lives here, then it has to push forward to a class to the right class that lives here. So this is the projective limit. But what I'm interested in is not exactly the projective limit, but rather the inductive limit. So these are classes that live in a fixed model. So those are elements of the inductive limit. So why? Because I want to just take my ample class on X and start pulling it back and calculating intersection numbers upstairs, okay, in a finite model. So if I have F, the nth iterate of F, I will compute my intersection numbers in Xn, the model that is obtained by pullback n times. And so this terminology was, in fact, is due to Manin, but was, this construction is due to Manin, originally due to Manin, but the terminology was done by Chokurov later. And in dynamics, it was used by Blanc-Cantat and Buxom, Favre, and Johnson to study Cremona transformations. Okay, so now let me tell you how. So you have this vector space. It's good because it's a vector space. The problem it is infinite dimensional. So, but let me tell you so how the pullback works. So if you have a model xj plus 1 that maps to xj, and you had a map vj plus 1 here, and the model xj here, xj plus 1, you had the map, you take a class alpha j in here, and you define the pullback of this class alpha j to be the one that is induced by the pullback by vj plus 1 of alpha j. So alpha j lives here, and you pull it back and you get a class here. So and this gives you a class on the inductive limit, a Cartier class. Okay, and doing this, it's kind of a trick, but it allows you to pull back, And here's now the strategy of our construction. So we have defined a vector space that is like infinite dimensional, and we still want to compute norms. Norms for which we can define spectral radius, and the spectral radius has to be those dynamical degrees, like in the regular case. So once you have this space of Cartier classes, then you're gonna define two norms. So of a norm on divisors. So ones that we denote, so the completion of the space of divisors with respect to this norm will be denoted N1 sigma. Then you will define a norm on codimension 2 classes. So this is a second one, a priori different. Then you have to verify that the spectral, okay, so it's the spectral radius here that I want to show. So that the spectral radius of those that the pullback induces a bounded operator whose spectral radius is lambda 1 in codimension 1 and lambda 2 in codimension 2. And then because I want to make my Hodge index argument, I want to check that I have a good intersection theory. So I want to be able to intersect two guys from the Banach space of codimension 1 and obtain a guy in the Banach space of codimension 2. And once I have this, then prove a suitable version of the Hodge index theorem to get the simplicity of the eigenvalue. Okay, like in the exactly like a little bit like the argument that I showed in the regular case. Okay, so that's our goal, and so let me tell you the way I'm going to define the first norm on divisors, on b-divisors. So you start. So let me tell you what was done in the case of surfaces. So in the case of surfaces, there was a construction due to Buxom, Favre, and Johnson, and they defined a Hilbert space. So how does it work? Their idea was the following: you start with a surface, and you look at the Hodge index theorem. It tells you that the space of the Néron-Serveri group endowed with the intersection product has a signature that is 1 and the dimension -1. And you take an ample class and you normalize it so that omega square equals 1. Okay, and what happens is like any class, well, can be decomposed with respect to this somehow signature. So you have the part where the intersection is positive and the part where the intersection is negative. Okay, and they define the L2 norm by making somehow the intersection product become positive. So you take the square of the positive part but you put minus the square of the negative. So this gives you somehow a Euclidean norm if you are in a finite vector space. And if you go into infinite in the space of b-divisors, so in this limiting construction, in this inductive limit, you get the Hilbert norm. Okay, so that's construction of a Hilbert norm. So our idea now is to apply this idea to get a norm, a Banach norm for in arbitrary dimension. So now you assume that you have x of dimension d bigger than 3. Then the way we construct this norm is we do, okay, you take alpha, and you take an alpha, a divisor. What do I want to do? I want to be able to restrict alpha to any surface to make my Hodge index theorem argument work. So you look at the restriction of alpha to a surface. This gives you a divisor on a surface. So now you can once you have a divisor on a surface, you can calculate the Booksom Favre Johnson L2 norm. And once you have, and you want to do it for every surface. So this is what we do.
Can I ask you? So here in your spaces xj are different, right? So then, but you have a common surface for all of them, or you take one surface and then you take the strict transform, or what do you do? The
So,
surface S, because it.
Yes, this is why exactly. So you have to take the strict transform. So this is why I asked that my surface are not like too bad. They have to be moving in good families. So this is exactly the condition, like to be base point free, to be able to do this. Okay, so it can happen that your surface, and so I take all the surfaces that move in a good way, and when you say move in the good way means base point free, and this is the notion invented by Fulger and Lehmann. And for all those surfaces, then you can do this.
So you take some surface S in X in your original.
No, in all the compactifications, in all the in my tower, in every model. So yeah.
But then if you push forward, then you get some surface from your original.
Yes.
Right.
Yes, but you want all of them, because you want to define a norm. If you only know how to build surfaces on one fixed model, it's not sufficient to get a norm somehow. If you have not enough, so you really want a norm, because it's a norm on the space of divisors on every compactification. If you only check for
I mean, there's come from one original one, and then you just put
not necessarily. By this definition, it's super for all those S.
Yeah.
So they live on.
Then you can always push it down to the original space of your place. So I mean, even you have S in every things, but then you can always push it to the original one, right? And then you get some surface from there, and then you just try to say that you take surfaces from there, from the original X, and then they are kind of free, so you can take strict transform.
Yeah.
Right?
Yeah. I mean, the problem is that you forget some things. When you're base point free upstairs, it's hard to build a base point free class from downstairs that gives you something base point free upstairs. I don't know exactly how to make this argument, but you're probably right that I might be able to do everything in S. But the thing is that my classes also live upstairs too, so I need to be able to do the calculation in every model too. So for me it was convenient to do for us. Sorry, convenient to do this everywhere. And so this notion of base point free surfaces, when you're on a dimension 3 variety. This is just the space of nest classes. Okay, so for us, it's this base form free notion is like the good generalization of ampleness, but for codimension K. The suitable generalization of ampleness. And so this is basically the way we define the norm, and we have to check that it induces a Banach norm, and
is it clear that it's a finite number?
Yeah. I mean, no, it's not clear, but yeah, that's what you have to check. I mean, that's what we check. Yeah.
Okay.
So basically, you have to normalize. That's why we use.
Yeah, I see.
Otherwise, it can blow up if you don't normalize correctly.
Yeah, sure. Okay, thanks.
Okay, so now we have this this norm in codimension 1 for divisors. Now I want to build a norm that in dimension 2. So the observation is the following: if you have alpha and beta 2 divisors, alpha times beta gives you a codimension 2 class, and the observation is that if you start with a base point free surface, so as in like as previously, then you can calculate the intersection of alpha times beta times S by restriction, by taking the restriction of alpha to S and intersect it with beta restricted to S. And the observation is that, well, if you see this formula on the right-hand side, well, you can apply Booksom-Favre and Johnson's theorem, which says that, well, the intersection product on L2 of S was B continuous. So it was continuous in the two variables, and it gave you a number. So that's how you can get the right formula for the norm in codimension 2. So you take alpha codimension 2 class, then what we do is that we say, okay, let's take the supremum over all the surfaces, base point free surfaces living in all the birational compactification xj. We normalize them correctly, and we take the absolute value of the intersection with that surface. Okay, so this gives you a number, and you take the supremum over this, and it induces the norm on this place in this space of these Cartier classes, and then you're going to look at the completion of these Cartier classes with respect to this norm, and it gives you another Banach norm. And you see that everything is encoded so that the restriction argument that I told you about in the regular case is going to work, basically because it's made in it is included in the definition in a certain way. Yeah. Yes.
Okay. I see. So how can you define a norm on N3?
You can try to define basically the same type of norm. Take the space of all varieties V that are base point free, and then intersect it with V, and it gives you a number. And yeah, the problem is that if it makes sense, if it not that it makes sense, that you can say something that can study the pullback operator. You can study the spectrum of the pullback. So you can define a lot of norms, and the main issue will be to check that you can say something about the eigenvectors and the eigenvalues. Okay, and we did the same. There's the same definition in arbitrary codimension of this norm, and yeah. Okay, so let me tell you exactly what happens if you choose these two norms. So the first norm in codimension 1, that's the one I denoted N1 sigma. So sigma means for surface, because we cut out by surfaces and we calculate the L2 norm. So that's why we denoted N1 sigma. So you take this pullback operator on N1 sigma. It's a bounded operator. And our theorem is the following. It's exactly the picture that I drew before, is that you look at the spectrum and there's lambda1 of f here, and the other eigenvalues of the spectrum of f is contained in the disk of radius square root of lambda2 of f. And you get a decomposition of the Banach space into two terms, this a complement, and a space of dimension 1. And on this space of dimension 1, this is an eigenvalue for an eigenvector for the eigenvalue lambda1 of f. And on the complement, you get an action that is that has spectral radius smaller than square root of lambda2 of f. So this eigenvalue is now simple. So it's exactly like in the regular case. And once you have this this statement, then you can deduce that the degree of fm, when lambda1 square is strictly bigger than lambda2, grows purely exponentially. So it follows from this statement, basically. Because you start with the class omega, and you start pulling it back, and you calculate its norm in n1 sigma. And this norm is going to grow like the degree of fn. Okay. Should I go to the next thing?
Well, I have a question before. So this theorem C is basically by construction, by the way you constructed the norms, or it's hard to prove. No, it's hard to prove.
No. So it's so once you have the norm, then you have to study the spectrum of f star. Okay, and what I said is formally, if I go back, you can formally, once you have the intersection product between n1 sigma and n1, you have an intersection product and the Hodge index theorem. I assume that you have, step 4 and step 5 are done. Then you can look at the argument that I did for the regular case. Mm-hmm. This argument here, and it's going to work like how do I say, copy paste. Okay. Yeah. And this is going to tell you that if you have two eigenvalues that are bigger than square root of lambda2, then they are equal to lambda1, basically. The main issue is that it's only half of the story. It's only half of the story because once you have that the spectrum is, this is an isolated value of the spectrum, you still have to show that well, first you first have to also construct an eigenvector. So it's not easy to construct such an eigenvector in general, and you need to have some good compactness properties. So I didn't say this here, but
okay.
And usually if you think of a bad norm, if it's too, you're gonna lose one of the things. If the norm has too good compactness properties, then you're gonna have compactness, but you are not going to be able to show the uniqueness of the eigenvalue. You're not going to be able to prove the Hodge index theorem. In fact, what happens most of the time is that you're not going to be able to even intersect two divisors, two generalized divisors. And if you do a too good norm, if you are able to do this intersection product and it's too good, then you lose compactness properties. You cannot extract subsequence. So that's the game that we play here.
Okay, thanks.
Okay, so let me go to the next thing. So in fact, what we prove is something a little bit, so the title of my talk is called the Spectral Interpretation of Dynamical Degrees. And so I want to go in a more to finish with a comment. Let's basically. So in the case where a lambda1 square is strictly bigger than lambda2, what we showed that the resolvent, so the inverse basically of z identity minus f star acting on n1 sigma, this gives you somehow an analytic function with values in the space of bounded operators in n1 sigma on this Banach space. And what we showed actually is that this resolvent has a meromorphic pole at z equal lambda1, and this pole is of order 1. Okay, and you can say it equivalently. This sequence of this analytic sequence is also has a meromorphic pole of order 1 at z equals lambda1. Okay, and I want to state a stronger version of the conjecture that I stated previously. That was about, you know, that the degree grows in between an exponential or a polynomial times exponential. So one stronger version of this conjecture would be to show that in general, this resolvent operator is always meromorphic, always has a meromorphic pole at z equals lambda1 of x, and then one would deduce that the sequence of degree would not grow faster than polynomial times exponential, where the polynomial term comes from the order of this meromorphic pole. And so that's what I wanted to say today about this this problem.
Okay, yeah, thank you very much for very interesting talk. Any questions? Further questions? Yeah, so can you go back to maybe 2 or 3 slides? Yeah, this one.
Yes.
So here you need to prove that degree of Fm is the same as the norm of Fm star on your n1 sigma space, right?
Yes.
So how is it easy to see? Or?
Yes, yes. Basically, it is okay. If you look at the definition of the norm, here, you see basically S is like a complete intersection. Okay, you have to imagine like S is like a complete section. So it is like omega at the power d minus 2, basically. And alpha times S, alpha restricted to S is like alpha times omega d minus 2. And then you calculate the L2 norm, so you plug it in here in this formula. And what will only count is this term, basically, because this term won't count. So you have, this is a, okay, let me write the norm. It's 2 alpha omega squared minus alpha squared. So this is equal to this, basically. So in this case, what I read from this norm will be 2 alpha omega times S. So let me write omega S at the power d minus 2 squared minus alpha squared omega S at the power d minus 2. So I read it a little bit like this. You see, this is basically, and you have to take the soup over some S that are based on free, but you have to imagine that it's like taking the soup over omega S at the power d minus 2. So now if you look at this and you replace alpha by the pullback of omega, you see exactly what you need. You don't care about this second term, minus alpha squared, but well, this is a positive. So basically everything is smaller than this term. And here you see exactly the degree square, sorry. If it is,
yeah,
if it is clear enough, yeah. And so the checking this is usually never problematic. Yeah.
Okay, I see. So can you go go back to norm. So you have two different norms, right? For norm n1, you have
Yes.
have a Hilbert space, and then for the other norms, you only have a norm. You have a Banach space somehow.
Yeah, for both you get two Banach spaces. Yeah, exactly.
Yeah, but for the other one, you have also intersection of two divisors, right? Type inner product of
Yes,
divisors. But for
exactly.
from n to you don't have.
Sorry.
But for n2, you don't have kind of inner product.
No. I mean, I don't know how to do that yet. Yeah.
Okay. And why? So can you go back one more slide to n1? So for n1, it's not possible you define a norm on n1 like what you define on n2. That is, you define the norm to be subprimum of alpha intersect with the curves.
Yes. Yes. You can.
Yeah.
It gives you a norm. It gives you a Banach norm, and actually you have we show later on that this n1 sigma, so this first norm, is included in the norm, is injects continuously inside this second norm that you just mentioned, this normal supremum of alpha times curve. Yeah, exactly. So you can, and
can you get the same result, or
we don't know how to if you take the supremum of alpha times curve, basically what happens is I don't know how to get the intersection product here. I don't know how to get the inner product to get an element here. So I mean, perhaps someone can do it, but I don't know how to do that, and it didn't work out for us in this case. And I have reason to believe that it won't work actually. Yeah.
I see. So then it means that now you only can bound lambda 2 by lambda 1, and you don't possible you cannot like kind of bound lambda 3 by lambda 1, right? But you cannot just say 3.
No, I don't know how to intersect 1 and 2, for example. I don't think in dimension 3, I don't know how to intersect this guy with this, maybe, yeah, with even this guy. Yeah. And,
Okay. So yeah, so one last question. So here you only use blow ups, right? So how about you use like alterations? Do you get the same thing, or maybe some bigger thing? Or
so you want to do in positive characteristic?
yeah, for example.
Then yeah, I don't know how to do it in positive characteristic.
So where do you need exactly that you blow up here? Where do you need blow up? Because it seems that if you have like alteration, you still can define some kind of this.
But you work directly on correspondences then you leave the realm of so even in even in the definition of the space of b-divisors here, you need to work in the space of all, not birational transform, but generically finite transform of your variety. So at this stage you cannot work already. And
Why cannot? Because you just define some limit, right? So why?
But then then I don't know how to check functorial to define the pullback, for example. Maybe the pullback will be more complicated. And then you have to take care of the second, the advantage with this construction is that basically you kind of don't care about this pi1, this projection on this side. You just start working with correspondences, then you have to work with both to remember both somehow, both projections. And
Yeah.
so I don't know how to work this out. Perhaps it's doable. Yeah.
Okay. Yeah. Thank you. Any other questions? Yeah. If not, then thanks Bob again, and thank you everyone for attending and speaking in this conference and workshop, and then hopefully maybe next years when the situation is better, maybe we can have a physical version where we might have some more updates, and okay, have a good summer. Yeah. So thank you. Bye bye.
Bye.